Well, good morning, everyone, and welcome to the BDR webinar series. My name is Monica, and I am part of the marketing team here at EDB. I will be your host for today's session, Replication, Performance, and Why It Matters. This is a very popular topic, and we are having this session for the second time. I am joined by Simon Riggs, PostgreSQL Fellow here at EDB. Before we start, I just want to go through a few housekeeping items. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have any questions, please feel free to submit them in the questions panel located at the bottom of your screen. Today's session is scheduled to last 1 hour, and we expect the presentation to last most of our time today, and we will allot any extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with any attendee whose question was not answered. And now, without any further ado, Simon, over to you.
Thanks a lot, Monica. So what we're going to talk about this morning is high availability and replication. And specifically, the point that I'm going to address today is replication performance and why it matters. Okay, a lot of people don't actually know that much about replication, and so there's a tendency to ignore it, right, and just sort of like go, yeah, it kind of works somehow, and we won't worry about how it works, and that that is distracting, and it's actually not very useful in many ways as well. So so what we're going to talk about is different types of replication, how they behave, and what the impact of those differences are on you and your applications. And that's particularly important, obviously, because it's all about the data, it's all about the application. So Postgres replication started probably 20 years ago. Different people trying to work out how to make Postgres highly available. And the first two serious production systems with Postgres were Sloaney, and then following on from that, Londeast, a sort of simplified version of Sloaney. And these were trigger-based replication. And then over time, we moved to physical file-based replication based on the changes in Postgres 8. And that was working fairly well, but what we had a vision is that we wanted to improve replication, and we wanted to make the physical replication stream the data direct from one node to the other node. And in Postgres 9 in 2010, we delivered physical streaming replication, and that's really been the main replication technology in Postgres now for over a decade. A couple of small problems with it along the way, but it's been mostly improving over time over that last decade. And then in the last few years, we've also moved across to logical streaming replication, which works slightly differently, and I'll discuss how those architectural changes have come about. But you can see from this diagram that I'm saying that the idea here is that replication is evolving from primitive forms to much more advanced forms that will help us. Okay, so Postgres replication continues to evolve to the present day, and there's a variety of changes taking place. But the important thing to discuss is why does it matter how fast replication is? Why does it matter how fast persistence is? Well, the key thought and the thought behind this whole presentation really is that the more robust and more highly available your systems are, the slower they go. And that means that when you're designing an application, you need to be aware of the speed of the replication, because that determines how fast your application will be able to go. Now, for some applications, if you've got a reference data application that doesn't do that many transactions per second, then you might have the absolute highest levels of durability. But if you have the need for a very high volume transaction system, then you might need to consider using other forms of replication that are faster in order for you to meet your needs. So what I'm going to do now is start describing the way that in Postgres we can control the choices that we make between durability and performance. And the heart of that is a parameter called Synchronous Commit. And that parameter has got a number of different settings, and depending on how you set that parameter, you get different durability and performance. So the basic idea is that when we issue a transaction commit, that is designed to ensure that the changes that you've made during that transaction are durable. And what Postgres does is it will flush the write-ahead log, which is what we call the transaction log in Postgres. That will be flushed or f-synced to disk before you are told that the commit has been successful. Okay. Now, it's interesting to note there that we only flush the transaction log. We don't actually flush to disk all of the changes made by that transaction. We do that more slowly over time. So that's just a way of buffering those changes to disk. But the transaction log, or the WAL, does get flushed to disk. Now, this is the default setting. And what I'm going to talk about now is what other settings that you have available to you. So if you set synchronous commit equals off, then that means report the commit before the changes have gone to disk. And in some cases, transactions can be up to 10 times faster if you use this particular option. Okay, now test it with your application. Don't just set it and assume that it will be incredibly quick. So it's faster, but if the server crashes, then the commits that you've made will not be pushed through to disk. Okay, and that's possible then that you may lose data. Possible because we also need to consider what happens with regard to replication. So if we set up a multiple node cluster where we've got the origin node or the master node and it's replicating changes to a second system, then that's what we call a replicated cluster. If we want synchronous replication, where the changes from the commit get sent to the second node before we reply to the application, then that is known as synchronous replication. And we can request that by saying synchronous commit equals remote apply. So the changes will be actually applied to the second node before we send an acknowledgement back through to the origin node. So this can be much slower because we need to wait for the round trip between the two nodes. And depending on how far apart the nodes in your cluster, then that will obviously make a difference to the performance that you get from this form of synchronous rep. Now, one of the things that can happen with synchronous replication is that your application just stalls while it waits for the round trip to occur. Okay, now that means that the latency or the execution time of your transaction will go down while we're waiting for that. Now that is unavoidable. What you can avoid is a drop in throughput, because it's possible that you can use more sessions to connect to the database, and that those more sessions are then able to do useful work while you're waiting for the transactions to be committed using synchronous replication. So if using synchronous replication slows you down, then you should just use more sessions to connect to the database. Now, the really good thing about synchronous replication is that it restricts the application from going too fast. Now, this actually then can become a problem, and I'll talk about that in a little bit of time. So another option that we have is synchronous commit equals remote write. Now, this is a form of synchronous replication as well, but it has a performance boost. And again, there's a trade-off here, because the performance boost comes at a slight cost, because instead of applying the changes on the replicated node, we only receive the changes. Okay, now that makes it slightly quicker, but it also means it's slightly less robust, because if the standby node crashes at the same time as the origin node crashes, then you would lose data, because it hasn't yet written those changes to disk on the second node. Now that is quite unlikely, okay? Because it's unlikely, it's often taken as a performance boost that you can apply to your applications. Now, the good thing again about this setting is that it gives a fairly consistent replication lag, because the application is unable to initiate new work until the changes have come back, or the changes have been acknowledged by the second node, and that again is particularly important. So a later option is synchronous commit equals local. Now, if you use this option, then the replication doesn't wait at all for a response from the remote node. Okay, as soon as the transaction log has been flushed to disk, then we immediately reply the commit was successful. So it is basically assuming that the performance of one node is the same as the performance of a replicated pair. So this is much faster, but it begins to become dangerous, because if you do this, then the changes can begin to build up. You can have something called replication lag, where you've made so many changes on the origin node that they can't all be pushed across quickly enough to the standby node. And actually, if you're not careful, then this can cause a backlog to develop, which can cause problems with data loss at failover. So let me give you an example of that. If the server is capable of performing 100,000 transactions per second writes, and replication is only limited to 25,000 transactions per second, if the application exceeds that threshold of 25,000 TPS, then a backlog begins to develop. So if the app runs at 75,000 transactions per second for an hour, then a backlog of 50,000 transactions will develop, which would take 2 hours to clear on a quiet server, and even longer in other cases. So at failover, much data would be lost if this is not correctly managed. So replication performance is very important for your data, because if you don't understand this example and you just use the high performance asynchronous replication, then you're going to cause yourself a lot of problems in your application. Okay, so this is really important that I'm able to get this across to you. So what we're going to do is have a look at some of the architectures behind replication and work out exactly how they affect performance. Before I do that, I just wanted to emphasize that the options that I'm giving you here, synchronous commit, all of these different options can be set in the PostgreSQL.conf file, but they can also be set within your application program. So actually the application program can choose what type of durability it wants for specific transactions. So if you've got an application program that's making changes, some of which are low value, some of which are high value, then you can actually choose to run some of the transactions at a fast rate and some of them at a slower, more durable rate. And this is particularly important. Now, it's important to note that this is an option that is not available in Oracle. And a lot of people assume that, Oracle and Postgres are identical, but actually it's not the case. And that because Postgres offers you this capability of having different levels of durability in an application program, or for different users, then that actually is an extension that Postgres has over and above what is possible with Oracle. So let's go on to look at the replication architectures and the type of performance that we get from them. So with trigger-based replication, users make changes and they insert data into shared buffers, but they also send data to the WAL or transaction log. So you can see these double thin arrows on the left of my screen. So the box on the left is the origin node, and we're sending data across to the target node or downstream node. Now with trigger-based replication, data is read from the database in batches, and then it's sent by a sender process across to an apply process on the downstream node, and then changes are re-executed on the downstream node. So this causes a lot of overhead on the origin node and a significant amount of overhead on the downstream node. So not only do you need to set up triggers to make it work, but there's a high overhead for the execution time for this mechanism to work correctly. And that's why we have brought to you physical streaming replication, which works in a different way. Here we read the data from the transaction log by the WAL sender process, and then we send that data across to the WAL receiver process, which writes it to disk, and then the changes are read from that file and applied to the database. So in that way, the overhead on the origin node is significantly reduced because we're only reading transaction log data, which can be written and read at quite a high speed, and also the apply process is particularly efficient. So this is much more efficient, and this allows us to go a lot faster with our replication than trigger replication allows, which is very, very slow. Okay, so this physical streaming replication, introduced in 2010, has been the main form of replication used with Postgres for the last decade. Now, with logical streaming replication in Postgres 10, we have an architecture that takes some parts of the design of physical streaming replication and a small amount of changes from trigger-based replication. So we're taking the WAL, the transaction log, we're reading that, we're actually decoding that into a set of logical messages, and then we're passing that across to the downstream node, and then we're applying those changes directly to the database. So in this form, we are not needing to re-execute SQL, so the overhead on the downstream process is reduced, and because we're reading the transaction log on the origin, that is also fairly efficient as well. So this form of replication is not as efficient as physical, but what I'd like to do now is just sort of go through the different types of comparison that we can make between these different types of replications so that you can understand them. So this is talking about the overhead on the origin, the amount of network bandwidth that we use, the number and type of the processes that perform work, and also the type of the apply mechanism used. And what, in terms of the differences between these, you can see that logical streaming replication is actually more efficient in terms of network bandwidth, but it can actually be harder in terms of the apply process. So there's a greater overhead on the apply phase with logical replication, and that's one of the reasons, for example, that in BDR we've actually got the parallel apply feature, which alleviates some of the overhead of doing the apply work. So what I'd like to talk about now is then what some very large database issues that can occur with Postgres replication. So with physical replication, row hints are not passed across as WAL records in all cases. And what that means is that if you execute a query on the standby node, then the indexes cannot fully trust that an item has been deleted. And so what can happen is that if you've got a table that's got a steady stream of updates occurring on it, then index searches on that table will be slower on the standby node than they were on the origin node. And in some cases, that can be extremely noticeable as a performance issue. Now, obviously, the bigger your database and the higher volume of transactions that you use against your database, then this will become more and more noticeable as a performance issue. So in order to maintain good performance for replication, the working set of the database must remain in cache. So that means that you need sufficient RAM on your hardware to allow the replication to work correctly. So if you don't have sufficient RAM for shared buffers for replication, then if something is not in cache, then that means it becomes I/O on those servers, and you'll need to spend more money on the I/O performance in order to get the database to replicate correctly. So there's obviously things that you'll need to consider about physical replication and full page writes, and also about logical replication as well. But the main and the simplest rule that you should follow is that the hardware of the replica nodes should always be identical to the hardware used on the origin node, because otherwise, when you fail over, the replicas may not be able to keep up with the original performance that it had on the origin node. So that's obviously an important point that we need to consider. So make sure the hardware of your replicas is the same as the hardware of the origin node. So the next thing to look at is the type of apply mechanism. If we are using physical replication, then we pass across the WAL records directly from the origin node to the replicas. When we make changes, there will be direct block access. Now, there was some talk that there was going to be a prefetch mechanism added into Postgres to speed this up, but actually that's not made it into Postgres 14, and so that might make it into Postgres 15. We don't know yet. Okay, obviously Postgres 15 is still being developed. Postgres 14 is going to be out in the next couple of weeks. So in terms of logical replication, the changes are made by executing searches against the primary key. So an update statement or a delete statement will need to search using the primary key before we apply the changes to those data rows. And that means that primary keys are currently all B tree indexes, and the larger a B tree index becomes, the slower the search will be against it. And that has what we call a time complexity or of the order of n log n, not log n, which means as the index gets bigger, the time taken to descend the index gets longer. Now, hash indexes do look like they might provide a much faster access mechanism here, because hash indexes essentially stay the same speed to access them no matter how big the index, and that's why hash indexes become more important for logical replication, and that's one of the reasons why I'm spending a little bit of time working on unique hash indexes as a feature. So at the moment, physical replication is more efficient, faster than logical replication, but of course that's one of the reasons why BDR has spent some effort speeding up logical replication so that the BDR performs very well. So this is the bit where I go and do some scary maths with you. So if maths scares you, then you know, plug up your ears now. But there's no problem really to understand what is happening here. So earlier I gave you an example where if you had a transaction rate on the origin node that was going faster than the rate of replication, then we would be able to see that there would be a lag developing. And what you can actually do is you can calculate the catch-up time using this small bit of maths to work out exactly how long that catch-up is going to take. Now, this applies to both base backup and catch-up. So when we initially create a replica, we do a base backup, and then we allow that base backup to catch up with the other nodes. Now, the same thing also happens when we do a failover between an origin node and a replica node, in that the the standby needs to catch up with any lag that has occurred. And this is the equation. What this is saying is that the processing rate of the maximum processing rate of replication minus the actual transaction rate from the origin node is the main thing that affects the catch-up time. That is the effective processing rate. So what we're trying to say is that the processing rate of the application needs to be less than the maximum processing rate of replication. Otherwise, a lag will develop. Okay, so it should be a fairly straightforward piece of maths for people to understand. The the issue comes when people haven't even heard of this, they haven't thought about it, and they're wondering what they're going to do about it. And so this equation is really the main reason for the talk today, because it's important to understand that if you have an application that is running at a faster rate than replication can cope with, then you will cause replication lag, and replication lag becomes data loss at the point of failover. So when a failover happens and you have a replication lag, then you're going to get data loss of some kind. And we don't like data loss, so we need to take note of what's going on here. So the next thing really to think about is how will we do major release upgrades without downtime, because it's really only logical replication that gives you the capability to upgrade the database without downtime. Now, sometimes logical replication may not be fast enough for you, but the real question is can very large databases rely on physical replication for their upgrade? And obviously the answer is no. So the question is, what are you going to do about your upgrade path? So the logical replication technology is specifically designed to allow the upgrades to take place. So what I've done in this talk is I've covered a number of different topics, and I've tried to make it clear that there are some important aspects of replication that need to be understood by application developers if they are to avoid data loss. So I hope I've explained these briefly. I know I haven't explained them in full, but what I'd like to do is ask for questions, and then I can go back and explain some details again a little bit more clearly in particular areas. So if people have got some questions, then please now ask your questions so that I can work out how I'm going to answer that. So questions, please.
Okay, thank you very much, Simon. So for all our attendees, they can use the Q&A tab for further questions, and you can start typing them now. Okay, so for now we do not have
Perfect. No questions.
any questions.
Perfectly explained.
Yeah, I think it was perfectly explained. Yes, I agree. Well, thank you very much, Simon, for the insightful presentation, and thank you everyone for joining. We will have the second session of the BDR webinar series next week, so we would like to see you there again. We will be sharing the recording of this session along with the slides in the next few hours. Okay, one question, yeah. I upgrade with logical replication supported on manager version change. I don't know that that's more of a
I'm
comment.
not sure what the question is there, but
yeah, I think it's more of a comment, but we will be talking about upgrading with BDR in the next session. So join us. We will love to see you there. And well, thank you very much. I wish everyone to have a lovely day.
Yeah. So yeah, hi to everybody. Hi, Andreas. Hi to everybody else. Thanks for listening. Hope to see you next week. We're going to do another session next week and look forward to seeing you there. So cheers, everybody. Have a good day.
Thank you. Bye.